Today we'll start uh, our discussion on rigid pavement design, and the method we are discussing today is Portland Cement Association method. Though there is another method, H2 method of pavement design, but those who are involved in designing this pavement, they found this method more attractive than H2 method of rigid pavement design, because it contains or it caters for the mechanistic method of pavement design in which stress and strains are considered. And it's an old method. It was first introduced in 1966, and the latest version is 1984. So latest is also, you can say, around 37 years old. So what is this method? Obviously, that I've introduced to you, it was published in 66 and later in 84. It can be applied to jointed plain concrete pavement, jointed reinforced concrete pavement, and continuous reinforced concrete pavement. The basic methodology, the basic method between the basic approach is, it contains calculation of critical stresses and deflections, and then it combined with the design criteria to develop design tables and charts from which we do our design. It's an extension of H2 road test method, and there is a design criteria. It is based on the performance, and these deflections you calculate, you consider here is the corner deflection, and we all know that the corner deflection is the most critical deflection while you design a rigid pavement. So what are the highlights of this design procedure? These design procedures that is being covered is not covered before by other procedures. That is, the degree of using a concrete shoulders adjacent to the pavement, and because the concrete shoulders helps in reducing the flexural stresses and deflections caused by the vehicle loads. It also considers the effect of using a lean concrete or econo-concrete, we say, subbase, which reduces pavement stresses and deflections, provides considerable support when trucks pass over joints, and provides resistance to the subbase erosion caused by repeated pavement deflections. Again, this method used two design criteria: the fatigue, that is to keep pavement stresses due to repeated load within safe limits and thus prevent fatigue cracking. Erosion, to limit the effects of pavement deflection at slab edges, joints and corners, and thus control the erosion of foundation and shoulder materials. Why we need this criteria? Because some modes of pavement distresses, such as pumping, faulting, and shoulder distresses, are unrelated to fatigue. To continue with this general concepts, they also consider triple axles. While the conventional single axle and tandem axle configuration are still the predominant loads on the highways, at those times in 1984, the triple axle was just introduced and was increasing. The selection of an adequate thickness is dependent upon the choice of other features, type of subbase, and shoulder type. With these additional design, the thickness requirement of design alternatives, which influence cost, can be directly compared. Now, what are the design factors? The design inputs start with modulus of rupture of concrete, subgrade and subbase support defined by small k. However, unlike H2, it does not consider monthly variation. There is a design period and they include traffic in terms of a load safety factor 1, 1.1 and 1.2. Depending upon the type of highways you are designing. Obviously, if you're designing a motorway, you take extra 20% traffic. And likewise, if you're designing a collector, it's 1%. And your question may be, do we design rigid pavement for local traffic? I can say yes or I can say no. Yes, because there are people very critical to it, but no, because it is not very economical. Now, how to do this traffic analysis in this method? So, how you calculate is that you always know the average daily traffic of the base year. Now, since you already know the H2 method of pavement design, you know what to do it. You multiply by the lane distribution factor, the projection factor. This projection factor, if you recall, that was G into Y in that, you know, in that thing that we were considering, you know, we have considered in while designing a flexible pavement. There is a directional distribution. You multiply it by 365 and the number of years. For instance, if a average annual daily traffic of a single unit truck, that is a 1.2 means 2 single axle truck, obviously single axle truck with the dual tires at the back, is say 3701, and I want to know the number of trucks in the design period. So just look at this thing, and I'm interested in designing it for 20 years. So the ADT is 3701. The lane distribution, assuming it to be 0.5, it can be any value. In the last example we have done, it was 0.9. So if it's a 4-lane pavement, you can say 0.9. And if it is, you know, a 8-lane pavement, this can be a 0.4. So whatever is the value you know from your previous knowledge, you can do it. I have taken this LDF 0.5 because in this manual they have said that this is actually what I'm sorry here. This is directional distribution, and that distribution is 0.55 now. It used to be 0.5 on those days. Then there is lane distribution factor is 0.93, right? And this is from the PCA manual I have shared. But don't worry, you can use that 0.9 that I previously shared with you in a H2 flexible pavement design. Now, where is this 1.6? It's, you know, if I'm designing, if the vehicle has a growth rate of 4.5%, then we take an 1.6, or 5%, we can also take this 1.6. So if you are designing it for 20 years, then 1.6, and 40 years, it will be 2.4. You know, when usually I teach this course, students ask me why there is no table for 10 years. It's because it is not feasible to design a rigid pavement less than 20 years, because then that the cost will be immense, and you may not have a full value of your money in terms of maintenance. And it's, when you compare the two pavement in terms of the maintenance period, so that's why we use this advantage of pavement design life for 20 years in this rigid pavement. Now, once you calculate this thing, then you have to distribute the traffic in terms of the axle. What is the load on the front axle, and the other is the rear axle. Now, this is in contrary to what you were doing in flexible pavement design, Pca method, in which you were actually taking the load on each axles and then summing the traffic. It is the other way around. In here, we estimate the total traffic over the period of the time, and then we distribute according to the according to the axles, front axle, rear axle, middle axle, whatever is that. So this is actually the protocols of this method. That is how you design this pavement for. Now, since there is a load, and what you do, there is, whenever you calculate the traffic, then you just multiply it by this factor 81.02. And where have this factor come from? Remember your basic lecture, kindly refer to it. That 1.2 truck had a fully loaded truck, had a front axle load of around 11.878 kips, and the rear axle load of around 31.847 kips. Now, for that, we will find a suitable truck factor, and that is for 1000 trucks. Where we want to know where in my equation 81.02 or say 0.28 at the bottom has come from. It has come from this table. This is a table that gives you the truck factors or the load equivalence factor on axles. Now, the load on my front axle of the vehicle was around between 10 to 12. It was 11.878 to be very precise. So the truck factor is 81.02, and this is a single axle load. That's why I have a single axle load of 81.02, and that factor I've divided by 100,000 because this 81 is for 1,000. So obviously for one, it can be, we have to do it by dividing 81 by 1,000. Similarly, I know my load is between 28 to 32. That was 31.87 something. So that's why I've taken 41.06 in that equation. Let's go on and just keep this, that one factor is 81, the other is 41. Oh, there's something. Actually, that was 31.84. That's 0.28. I'll check why I've taken 0.28. Oh, sorry. Because this is also a single axle load. I'll just calculate it. So because that was 28 to 30 and more than 30 kips were not allowed, so I've taken the minimum as 0.28. I was thinking that was tandem axle. So that's why 0.28, because the rear axle was also single axle. So that's why 0.28 was taken. So whatever is the traffic that I have calculated this figure, I have to multiply it by the truck factor because of this load, and truck factor because of this load that I have calculated from table 5 here. So if you would have tandem axle, obviously you will use this bottom table. For a single axle, you have to take this table, and likewise, we will discuss later how you take the factor for triple axle. So once you are done away with traffic, you will go with your subgrade and the subbase support. Now, the subgrade support, it is taken load in pound per square inch per inch, as we know, on a loaded area. The K values expressed pound per square inch per inch, we have already discussed this. Since the plate loading test is consuming and expensive, the K value is usually estimated by correlation to simpler tests such as CBR or R-bit test. Now the result is valid because exact determination of the K value is not required, and the normal variations from an estimated value will appreciably affect the pavement thickness. Now, to avoid the QADIR method required to design for seasonal variations in K, normal summer or fall weather, K values are used as reasonable mean values. Another thing is, we don't use untreated subbase for the sole purpose of increasing K values. Where a safe bus is used, there will be an increase in K that should be used in thickness design. And if the subbase is untreated carrier material, the approximate increase can be taken from this table, that is table 1. Let me show you the table. So if I take, now this is a simple correlation, you know how to calculate K from this relation. So if K is, CBR is 2, K is 40, CBR is 20, K is 243, so on, so forth. Now, if the value of K is say 50 and you are providing a 4-inch subbase, you can take this as 65. 50 increased to 65. Let me repeat one thing for you. When we design a rigid pavement, the subbase we already know or we already assume that. So generally, we don't calculate the value of subbase in a rigid pavement design. It's already understood and you already take it. You can have a 4-inch, you can have a 6-inch, you can have a 9-inch, and you go for 12-inch. So when you go for more thicker subbase, you have a more K value. Consequently, you may have a lesser thicker asphalt concrete required. So this is for untreated subbase. And if I go for treated subbase, now if I had a value of 50, that becomes 170. Look at this value. Even providing 12 inches subbase, my value for untreated base decreased to 110, while for treated base of 50, I will always get 170. So instead of going for 12-inch untreated base, I will prefer 4-inch treated base, and that we have also know from our knowledge of the previous lecture that what is a cement-treated base, what is a lime-treated base, and so on and so forth. So you know, this gives you an extra advantage of cement-treated base using cement. So you know, most of the designer, they recommend cement-treated base. We go on further. Now, the design criteria, as we said, that we consider traffic, we consider subgrade, and then we consider the fatigue analysis. Now, these fatigue analysis has been calculated, the charts have been developed, It is based on the H stresses midway between the joints, joint spaces, and type of load transfer. They do not consider the design methodology, no warping and curling stress, and that it's assumed that the magnitude of critical stress is reduced with providing a tight shoulders. And to add to your knowledge, there are different ways of tying a shoulder together. One way, if you have a concrete shoulder adjacent to the concrete pavement, now the things become easier, that you can have a dowel bar and that you can tie with the shoulder. But if you have a concrete shoulder, if you have a treated shoulder, then, or aggregate based shoulder, then you have to tie it with aggregate interlocking. It's just, you can assume a teeth coming out of the rigid pavement, and that teeth joint with an asphalt, so is with a treated shoulder, right? There are equivalent stresses calculated for single and tandem axles. That is why we were interested in distributing our traffic in terms of the single and tandem and maybe a tandem axle. Those values, the fatigue values, the allowable stresses, they have been given in table 12.6, 12 figure 12.12, and when I'm saying all these tables, you please refer to the to your handout, the manual that I have shared with you, the PCA manual 1984, and that's what I'm referring, that table 12.7 and 12 figure 12.2. By the way, this PCA method is also present in your textbook that I have shared with you earlier. You can also go there and you can get this. But remember that even that book, the textbook, it does not contain a comprehensive tables and all other relevant table as compared to this handout that I have shared with you. So I always recommend that you use that manual that I have shared with you. Then we calculate stress ratio factor. That is equivalent stress divided modulus of rupture. What are the allowable load repetition? This we can evaluate from figure 12.12. There is a percentage fatigue, and we want that the total percentage fatigue should be less than 100%. Because if it is more than 100%, it means you have a thinner pavement and you have to redesign your pavement or increase the thickness. Now, how you do about it? How you go about it? Now, this PCA method is a trial and error method. You have to start with some thickness. And I give you an idea. Normally, if you design a rigid pavement, normally the least thickness should be 8 inch. And what would happen that after the analysis, you find that thickness is less than 8 inches, I recommend go for the flexible pavement. There is no use of going for a rigid pavement that is less than 8 inch thick. This is my experience. Obviously, there is no code that can limit you. You can have 5-inch pavement or you can have a 4-inch pavement. But this is my experience while designing a rigid pavement. So normally, if you go for lesser thickness pavement, it will be very, very uneconomical, to say at least. Then we have to, there is a table, there is a worksheet that is present also on the back of this manual that I have shared you, and there are columns item 8 and 11 that we will see, and then we have to divide the equivalent stresses by modulus of rupture, determine the allowable repetitions from that figure, and compute column 5 by dividing column 3 by column 4 and multiply by 100, and add that value to determine the total fatigue. Then there is one more thing. There is a design criteria or erosion analysis. The base on corner stresses when axial load is placed at joint near corner. Type of load transfer mechanism has a substantial effect on corner deflections. Different erosion factors provided for doweled and aggregate interlock joints. Tight pieces shoulders reduce corner deflections. Erosion analysis considers a pavement to fail by bumping, erosion of foundation, and failure of the joints. The most critical deflection occurs at the corner of the slab when the load is placed at the joint near corner. Fatigue analysis controls the design of thinner pavement, residential secondary roads, regardless of whether the joints are doweled or not, while erosion analysis controls design of thicker pavement under medium to heavy traffic without dowel joints. And that's why, we do both analysis, and, you will have somehow compromise or, economical pavement, at least you say. Because if you are going for more pavement, thicker pavement, then erosion analysis will control that. And if you're going for thinner pavement, then fatigue analysis codes. So the total of them, if it becomes 100%, more than 100%, then you have to design. And if it is less than 100%, then you have to reduce the thickness. These are, the values where you will find this erosion damage, dowel, CRCP, dowel or CRCP aggregate interlock, and all those different configuration of the rigid pavement. So this is how you design. Same, use trial thickness, enter erosion factors, determine allowable repetitions, compute by dividing column 7 by column 3, and multiply by 100. All add values in column 7 to determine the total erosion damage. Now, this is the worksheet you have to know. How this worksheet, what are the columns or what are the rows in this worksheet? I go one by one. Obviously, it starts with the project. Obviously, that I say it's a project that we say, if it is a pavement design of northern bypass, actually it's a real design. Then there's the trial thickness. We started with 8.5 inch, as I show you that this may be 8. Then we have, the subgrade, subbase, subgrade, because we have provided a treated base of 4 inches, so it becomes 250. The modulus of rupture, as you know, it depends on 7.5 square root FC dash. So if you consider, say, 6,000 psi, and if you just take the square root and multiply by 7.5, you will get around this value. And since this is a northern bypass, it's a heavier road type classification, so we use 1.2 as a load safety factor. We say, yes, we have a dowel joint. We say we have no treated shoulders. We have designed it for 10 years, and we have designed it for treated board for 10. Remember, I told you that we don't go for 10 life, but for the sake of this example, we said 10 years, because at that time, we were told that you have to design for 10 years. Even though sometimes you have to do the works according to the specifications set by your client. So even though with my old theory of not considering the thickness design, we still go for the 10-year design life. Now, so this is, column 1, that was the axle load in Gibbs. We multiply it by load safety factor. We got expected repetition, and we find we have to calculate allowable damage, allowable repetition, then we calculate fatigue percent, erosion analysis, allowable repetition, and damage percent for single wheel, tie drum wheel, and tie drum wheel. Right. How you do it? So first, we are interested in knowing what is an equal stress and how I have got this 214. How I get it? So for that value, I go. Okay. So that is a table. If I consider this, say, as for concrete shoulders, so I've assumed my thickness as 8.5, and I know that actually what happened is that there I've written that it's a dowel joint, but there was no concrete shoulder. So assuming there is no concrete shoulder, I will use this table, and if I have concrete shoulders, I will use this table. Now, since I've assumed that 8.5, my equivalent stress is 222 for 200 and 206 for 300, and this is the value for single axle, and the other is the tandem axle value. So equivalent stress for single axle load is between 2222 and 206. So if you interpolate, then it becomes 214. Similarly, for tandem, it is between 174 and 193. Take the average because we have this value of 250. So that's how I got this value of 214 and 183.5. Once I know this value, the stress ratio is simply I have to divide 214 by 581. I will get 0.368. Similarly, for knowing the stress ratio factor, for tandem axle, I divide 183 to 581, I will get around 0.28. Right? Now, then there is an erosion factor. Obviously, I have to refer a table for erosion factor in the similar manner. Unfortunately, this is not there, but you have to believe me, these are erosion factors for the tridems, but you can have erosion factors for single and tandem axle. So that's similarly the way you have found equivalent stress for fatigue analysis. You always have this type of table in which you have thicknesses, and then you have this K values, and you can always find these erosion factors from there. So this is how erosion factor for tandem is calculated. Now, what you do next? We assume that we had a single unit truck in which first is a single axle, the other is a tandem axle. So for the first axle, we had this 8 kilo-pound on the load on the first axle. Then there was a truck. We have this single unit truck 1.22. Again, that was the front axle was 22 kip. And then we had a semi-unit truck in which that's the front axle that has got 1.22 front axle. So all of them, the first one is the single axle, 8 kip. I multiply this by 1.2 because we have to apply a load safety factor. So 8 becomes 10. 22 become 26, and again this 10 become 12 if you multiply by 1.2. Similarly, the other part of that axle was tandem axle, and it was I had a load of 16 kilopound, and then I multiplied by say something, and I got 86. And this 34, I'm afraid this load that I'm taking is not what is being reflected. It's more than maybe 72 or something. Maybe it's erroneously written here. And how you calculate the triple axle is you divide the total load on triple axle by 3, right? So if it is that had a load of 52, you divide it by 3, that's become around 15, and you multiply 15 point with something 1.2, you will get around 30 or 27.5. Once you do this, and this is the expected repetition, and remind you, this expected repetition we have calculated the first thing in our lecture. This is the expected repetition, like there. This is how we calculate the expected repetition. Likewise, we have done for this problem as well. So these are the values coming from there, and similarly, and this one as well. Now, once you do it, then you have to calculate allowable repetition, and this how you will do it is from this chart. I say unlimited. Why? Because, for example, I had this load of 10 and I have stress ratio of 0.368. So what I am going to use, this value give me the allowable repetition. So say for 10, this is a single axle, and if I have to find for tandem axle, I use this side of the table. So for the single axle, I will have to use this side of the figure, and for tandem axle, I will use this side of the figure. So say for 18, and I have a stress factor of say 0.38, I'll join it and extend it. So here I will get this 10 million Essel's value. For say 30, I will get this 10,000. Now, what would happen if I would have drawn say 10? Then obviously, if I join 10 with this 0.38, I will go beyond this value. So if you go beyond this value, you cannot estimate what is happening. For instance, what I'm trying to say for the instance 10 kip load, and if I want to join this 10 kip with 0.38, as you can see, I'm going up outside my paper. So for that, I say it is unlimited. What would happen on the contrary if I this 60, and if this I go say for 0.38, then what could I have done? Here, if I take 0, then you will have a mathematical problem. So for that, because 10 over 0 is infinity and you cannot solve the problem, if the line you find is below 100, just take minimum as 100. But if you feel this situation where you cannot connect this point with this line, and if your line is going outside of the paper, you take this value as infinity, or you say unlimited, because anything divided by unlimited, you can have 0 value. But if you have any value that divide by 0, that becomes infinity, and you will not able to solve the problem. So that's why I say for 10 it is unlimited, for 26 even it was unlimited, and for 12 it was unlimited. And this column fatigue percent is what? This expected divided by allowable, that's why 10 something 10,000 something or this divided by this, infinity becomes 0. That's why we have a 0 value. And unfortunately, you have all for this triple axle we have this 10,000. Otherwise, as I've shown, for 30 you can have this 10,000. Otherwise, you had an unlimited values, and that's why your fatigue percent due to single and tandem axle becomes total 0. But because of the tridem axle, you have some value. Now, in order to calculate erosion values, you also go use this chart. Now, this is a fatigue analysis chart, and this is erosion chart. Again, single axle, you will use this side of the figure, and tandem, and you just connect your this value for this value, and then you will get this value. I do it one for you. For instance, if you have 86, and then we have a stress factor of erosion 0.282 stress ratio. Erosion factor will use this value. Stress factor will be used for fatigue analysis, and for erosion analysis you will join 86 with 2 point something to get your allowable repetition for erosion. So let me see, where is 86? It's not in the table, isn't it? But for tandem axle, it's an 86. So let's see, insert line, and then for say 86, 2.08, and this comes some value. So this is how you will find the value of 200 million or something, and for even for 90 you take this value. Now this erosion factor again 60 something divided by this column, and you will get 0.302%, and this divided by 15 million, I guess, or 150 million, this you get. So total erosion is 17%. And if you add these two values, it becomes 77%. It means the pavement thickness you have selected is very good. 8.5 inch is taking care of the both fatigue and erosion analysis. And you can say, okay, this may be my final thickness. But mind you, for economical reasons, we may go for another trial. If we reduce our thickness, say for 7.5, and for 7.5, if I get the second 7.5, and if it becomes more than 100, then I see that my value is, if it is become 7.5 and this total becomes 99%, that's my final thickness. But if my thickness, by reducing the thickness 7.5, I get this total value of say 120, I'm not going to take this 7.5 because my pavement is getting filled. Anything more than 100% means your thickness is less than what you require. Anything less than 100% means though your thickness are adequate, but it may be uneconomical, so it has to be reduced. Now, I can address your concerns. What will be the acceptable value? There is nothing like 100%, but there are always ideal figures and there are always practical figures. So if your values are say between 90 to 110, that is 10% 10% error or 10% limits. If it is 90% or it is 110%, both you don't need to run a trial. Now, talking in context of the final exam, if you find that you have got this value, you have to go with the trial, only one trial. and then you have to comment. For instance, you are in the exam, you have assumed that 8.5 and you got 77. So now you have to repeat that design once. For instance, you say, okay, I'll try for 8, and it becomes again less than 100%. You leave the question with a remark that since it is, it has improved a lot, but it has not improved according to my desired criteria, I take this as a accepted value. That's it. Practically, you have to go between 90 to 110%. I hope that this you have understood the thing. So there is another thing that's in the topic. Why you always use this treated subbase? Why can't you use a lean concrete? That is, we as a structural engineer, as a civil engineer, we are fond of that lean concrete always in the foundation everywhere. So why can we take concrete, lean concrete uh, here as well? So my answer is yes, you can do it. But there is a different approach to this method. What is that approach? For instance, I said I will take, say, 6 inch of lean concrete. Here, we'll say this, there is a subbase that is a lean concrete base that is 4 inches, and I will take the subbase subgrade value with no addition. That is, if I had 50, I will use that 50. Unlike you, I'm not going to use the value, the modified value, because I'm not no more using that treated base anyhow, treated or untreated. So I will take this as no support, even it is untreated, because this is not untreated, this is a lean concrete base. So I'm not going to do this 50 value to another value. That's the whatever is the value of K I had, I will take this value here. So this is the thing. There's a difference, and we come up with some thickness. For instance, I came up with this same 8.5 inches, but obviously the K value is different there. Remember, we are not going to change. I keep on repeating, we are not going to change the value of K. Whatever you find the K with that value from CBR, like here, just for example, if I had a CBR of 20, I will use only 243, 10, 140, but I am not going to use this table anymore. I will take these values only. I'm not going to consider these values, any of these values, because I am not using a treated or untreated base. I am treating the lean concrete. Now, once you do this, and I presume that we have done this, then after my design, what I need to do? At the appendix of that report, find this table as well. So how you read this graph? So for instance, what are this? Why these? There are 3 sets of different curves here. So if you say, if you have, say, you have come up with the 6 inch lean concrete, 3 inch lean concrete, you may have, say, 4 inch lean concrete, or you may have a 5 inch surface. So if your modulus of rupture is between 600 and 700 psi, you will go from this side of the curve. And if your modulus of rupture is between 500 and 600, you will use this type of the curve. It's very easy. You see, what you need to do is, say, for in this problem, I had the value of 8.5 as my as a final thickness. So, and since my modulus of rupture was between 500 600 psi, I will use this side of the table. Now, for 8.5 inches, I can not have a luxury of using 6-inch subbase. I can use, I can use this either. I can use this value. Let me show there's something wrong with this. So I can either use 4-inch or I can use 3-inch surface. And what is these values? This is the modulus of rupture of lean concrete. So I draw a perpendicular 8.5 inch. So if my modulus of rupture is 250, my thickness will be 7 inches of total concrete, the main concrete, and with a 4-inch lean concrete base. Or if I am using a 3-inch lean concrete, and if my value is 250, then I'm going to take 8 inches. So what let me explain you once again. You see, I have not considered any support value while I was designing a main pavement. So once we design up, I have designed the whole pavement of 8.5 inches. I will take how much I can reduce by providing a lean surface of either 3 inches or 4 inches. So if I had 8.5 inches, by using a 4-inch lean concrete, I can now have 7-inch of my main concrete with 4-inch base, and or if I provided 3-inch lean concrete, then I could have say 8-inch of this lean concrete. Remember, my final thickness is also dependent upon how much good my lean concrete is. So if I'm using say 450 lean concrete, then I can have 6 inches main concrete with 3 inches. Or if I'm using say 350, I can have a 7-inch with 3-inch lean concrete. And if, for instance, I am using a 4-inch subbase, and I will not use 450 because 450 will be uneconomical. I will use 350 concrete, modulus concrete. If I will have a 6 inches and 7 inches if I am providing 250. So all these final values will depend. So if I draw a section, cross section, I will say, and I assume that it's a 250 psi 4-inch lean concrete. So my final cross section will be 4-inch of lean concrete with 7-inch of a main PCC concrete, having a flexural strength of 581 psi, and lean concrete having a flexural strength of 250 psi. So this is how you use this lean concrete. You can another way of doing this. This is a lean concrete subbase. So that's it with this PCA method. I hope you have understood it well. And since I'll be sharing this video, you can always go back and listen to this video and improve your concept.